My name is Andreas Reiter. I'm with Microchip's Power Supply Applications Group. The topic we would cover today is our new CIP Hybrid Power Starter Kit. This starter kit is introducing the PIC16F, 17.6X and 7X families of freely programmable PWM controller microcontrollers. These microcontrollers have specific peripherals that are running independently from the core and are highly configurable so that you can configure them or interconnect them in specific ways to form some PWM controller architectures. So the advantage of this freely configurable peripherals are that you can tailor the PWM controller capabilities specifically to your very application. To allow designers to utilize these capabilities, we also have introduced a new design toolchain, which is encapsulated in our development environment, MPLibX. So this is part of our Microchip code configurator tool called MCC, and is a set of sub-libraries that allows you to simplify the configuration of multiple peripherals at the same time. We have set up this assembly in this demo here, where we have the starter kit on the left, and here on the right on the screen you see this MPLibX environment with the specific switchmode power supply library set or subset for Microchip's code configurator. So this tool now can be used to set up PWM controllers that support different control modes like peak current mode control, voltage mode control, average mode control. You can combine multiple control loops. You can add in specific fault handlers, and the device itself then supports you with setting specific thresholds like shutdown levels for maximum currents, voltage clamping, input under voltage, over voltage lockout, and further features by utilizing the internal DACs. So the variety of things you can do with these peripherals is really, really wide. So the switch and power supply library helps you to abstract the capabilities and tailor them to specific topologies. So therefore, we also offer different sets of pre-configurations for targeting specific topologies. So once you have used that tool to set up a PWM controller for a specific application and topology, then you're generating the code. The code is downloaded into the device. The code that's generated with the device also includes functional aspects like soft start, so that you're having a nice behavior right from the beginning, so that when you fire up the power supply for the very first time, that you can be sure that it won't burn. So once you have downloaded it, and this is what we are doing in this demo set, is then we have connected a network analyzer to the output. We are injecting an error signal, and we're using our Bode 100 network analyzer to measure the total open loop gain in the closed loop system. So depending on the additional tools you might have used to design your power supply and to set up your compensation network, so to achieve a certain stability of your application, you can then just measure directly from the kit the final results compared with your simulation, and then you take it from there, and in further some iteration steps you might have quickly achieved your goal. So before we go into the details about this kit and the software and design toolchain, it might be necessary to explain a little bit what hybrid power actually means. The word hybrid is often used in different contexts, like hybrid power supplies is something entirely different from hybrid power controllers. So hybrid in our context means that it's a device which is somewhere between the analog control domain and the full digital control domain. So analog controllers usually come as fixed ASICs covering very specific topologies, very specific applications. So the conventional POL controllers, for example, or you have your switching regulator for flyback controllers or resonant converters. And for every single one of them, so for every single application, you might have a set of specific ASICs to choose from. While full digital control then digitizes even the feedback loop, so everything is running in software. The interface is an A to D converter, so analog signals, continuous time domain analog signals are converted into digital signals and then processed through software, and then some PWM is adjusted. So the latter one, full digital control, gives you extreme flexibility in terms of what a controller can do. While analog circuitries might have a significantly higher performance, but they are nailed to what they have been designed for. So that section between both worlds, that is what we're trying to cover with hybrid controllers. So that means we have a small device with relatively low power consumption, within the architecture, we are combining digital logic with analog circuits. So that we can leverage, let's say, the advantages of both worlds in one single device. So, and when we are focusing on these hybrid devices, then it's always a device which is targeting an application which have a specific requirement for very specific features. So the basic concept of these products is that in one chip you get a microcontroller core and a PWM controller peripheral. That PWM controller peripheral always breaks down into three major blocks, consisting of the compensator, so the area amplifier basically, and the modulator. So the modulator then determines which control loop, control mode you're applying, and there's always an additional fault level that helps you to make sure that the power supply stays within its safe operating range. The fault is usually tied into the modulator or uses inputs to the modulator to shut down the power supply in case something is going wrong. So when we're looking into the modulator, so here on the right side we see a specific setup for a voltage or an average current mode, and on the top we see an implementation for a classical peak current mode controller. So here on the upper right in the current mode section, we find a subset of labeled with PRG. So that stands for programmable ramp generator. So we are utilizing this ramp generator to generate a negative ramp which is modulated onto the reference input to our modulator. That then is used usually in peak current mode for slope compensation, but it can also be used in voltage mode. This is when you look below. You also see a voltage ramp on the upper right, where we use a positive ramp to generate an analog PWM signal. The next peripheral we find in this modulator are fast comparators. So in the current mode section on the top, we find that comparator between the ramp generator and our so-called COG, which is actually our PWM output logic block. So that comparator is used to tie in the current feedback so that we can trip on peaks of the inductor current. While in voltage and average current mode, that very same comparator is now used to compare the reference from the area amplifier to the artificially generated ramp, and when the ramp exceeds the reference voltage level, then it changes its output, trips an SR ledge, and this then influences our PWM output. So in both modulators, we always use a PWM module and the so-called COG, so the complementary output generator, or in other devices it's called a complementary waveform generator, CWG. What these blocks do is actually, so they give the capability to start out from a single PWM signal and split it up into complementary waveforms, allowing you to adjust dead times, or you can split it up to a full bridge drive. So it also offers additional inputs for fault signals. So fault triggers that come from different peripherals or from external circuits can also be fed into that PWM logic, and some additional glue logic then also would allow you to establish something like conditional fault handling. So the third level is the compensator. The compensator on these devices usually are just consisting of an air amplifier. So this is a general purpose operational amplifier. Then you get a DAC to adjust reference, and then the reference itself, which is called the fixed voltage reference, FVR. So in addition, to help you to condition signals, especially fault signals, to define fault levels to trip on, there is an additional set of comparators and a DAC with a lower resolution. So usually you get 5-bit DACs that help you to set up thresholds. That 5 bits might not be sufficient in some cases, so when you need a higher resolution, then it is possible to use external resistors to create a window which is then still scalable with 5-bit, and then you set it around a threshold range you would like to set up. So once we have picked these 3 blocks, we now can use these to set up an entire analog feedback loop. Here we see the first architecture. So on the right we have a power supply, so in this case it's just for the purpose or for the sake of an example, it's a boost converter that offers a voltage feedback coming from a voltage divider, and we have a peak current signal which is taken from below the boost main switch using a shunt resistor. So the voltage feedback now is fed into the outer loop portion of our architecture, which is then our air amplifier. So the air amplifier compares that signal to our reference, which is internally set by a DAC. The output of that air amplifier is fed into the programmable ramp generator, and this part we are modulating a negative ramp onto this reference voltage to apply slope compensation for our inner peak current mode control loop. Then we are entering we are taking this output of this programmable ramp generator, feed it into a comparator. That comparator compares that reference signal to the peak current signal that's coming from our shunt resistor, and then that output of that comparator trips our PWM output logic and effectively truncates the duty cycle. So to set up the switching frequency, we are now using a digital PWM module, which allows us to set up a fixed period with a maximum duty cycle. So in case the comparator does not trip the PWM module in time, it's still the time base of the PWM module, which makes sure that the duty cycle is not hitting 100% and maybe with a bad outcome when your inductor saturates and then your power supply is effectively going out of control. So one thing we see here in this particular example is because of these devices are highly configurable and can practically drive any kind of topology, it is very hard to define RC network values that might be necessary to set up an appropriate compensation for every single different topology out there. So therefore, all of the compensation networks need to be external with these devices. So we see here in the lower, around the OPA, so the operational amplifier, that the input as well as the output is connected to a device pin. So these device pins are usually sitting right next to each other so that it's very easy that you can place your RC components of the compensation network very close to the device. So after having established this basic feedback loop, we are now adding the fault level. So the fault level consists of a comparator with a 5-bit DAC. In this case, we are using it as an additional overcurrent shutdown. And then we can feed that output of that comparator directly into the COG so that it asynchronously overrides anything that's coming from the software, from the rest of the PWM architecture. And we can truncate the duty cycle and turn off the PWM immediately as fast as possible. So usually these comparators have a propagation delay of between 30 and 50 nanoseconds, and this is the time frame in which you can shut down can you respond to faults and shut down the power supply accordingly. So what we can do with these PWM controllers now is a lot. So as I said, potentially you can support all kind of different configurations for specific topologies. It does not only cover fixed frequency, you can also set up the peripherals to support hysteretic controls like constant on time, constant off time, quasi-resonant converters, resonant converters. So the variety of possibilities is really, really wide. So just to keep things simple, let's just start with fixed frequency operation of a standard topology. And this is what we are doing with this starter kit. So in this starter kit we have used a simple synchronous buck converter, not only because it's safe to operate and it's easy to compensate, but also because everyone is very familiar with this topology. So this starter kit now comes with multiple options so that you can play and experiment and explore a little bit the capabilities of the part, play with the different configurations and see how you can solve different design challenges by using different modifications of a preset of provided examples. So when we're looking into the hardware, we find that this board has a power supply on the lower side. So this is where we find our synchronous buck converter. So that buck converter has been designed for a power level of approximately 25 watts. So the maximum current you can pull from the output at 3.3 volt is roughly at around 8 amps. So here above, this is where we find our controller. So that controller is bigger than it would be necessary for that single topology. So we have picked our superset device providing up to 4 independent PWM controller peripheral sets. The reason why we have done that is to allow you to switch between different control modes. So we have set up one PWM controller for voltage mode, another one for peak current mode control, and a third one for average current mode control. We use the peripherals of the fourth one to add more advanced functions. One of them, for example, is DCR sensing. So one of the current feedback options provided by the power plant is a RC network, which is tied in parallel to the main inductor and which can be used to use a lossless sensing technique, which is fairly popular, especially in low voltage POL applications. To implement that function, we need an additional op-amp. So as the op-amp is still available from the fourth PWM controller architecture, we can now utilize it to create an additional option which then is tied into one of the other PWM controllers. So that kit now is supported by the power supply library, MCC. So when we are now trying to utilize this extreme flexibility of the peripheral, we really rely on tools which try to keep the complexity as low as possible during the design process. So for that particular purpose, we have created this switch from power supply library, which is available in the Microchip code configurator. So the basic architecture, so the ones of you who are familiar with MCC might know that it is a graphical tool that helps you to configure specific settings of one independent peripheral. So usually when you set up an application, you pick one peripheral like a UART, and then you use that GUI to set up baud rate or very specific details of that very peripheral, and then you are generating code, and the generated code is then called during startup of the device and putting that function provided by the peripheral in place. So now, as we have seen, that a switch from power supply controller is more than just one single peripheral. The configuration of multiple blocks can get very tricky. So eventually you might end up with 7 to 9 different peripheral blocks that need to be connected in a very specific way to achieve a certain function. So to simplify that design process, we have now added additional layers to our MCC design tool. So here on the bottom of that diagram, we see that classical MCC layer. This is what most of you are maybe familiar with. And this is what contains all the different configuration sets of every single peripheral. So here in that list, you see all the peripherals that are used to form that function of a PWM controller. So here we find this programmable param generator, the complementary output generator, the PWM module, a timer, comparators, digital to analog converters, fixed voltage references, op amps, and so forth. So these blocks now are merged into that functional blocks of a modulator, here on the left for peak current mode control, and a compensator block, which consists of an op amp, a DAC, and a fixed voltage reference. Here on the right we have another set, and this is the modulator block for voltage mode control or average mode control. So once you know which control mode you would like to use, then we can tie together compensator and modulator block to form a control mode block. In this case we have two options, peak current mode control or voltage or average mode control. Now this block is still very generic and is not really tailored to a specific topology. So to make the right decision on the switch configuration, which kind of dead times you need, we now need to nail down the topology you would like apply this control block for. So this brings us up to the next level, which is the topology level. And here, specifically for our starter kit, we are using a synchronous buck converter block. So that block now, when we pick one of these blocks, we know exactly what the PWM output configuration needs to be. We know which feedback signals we need to consider. And we can pick all the peripherals to form a PWM controller so that you as a designer end up with a system that is already pre-configured, and the only remaining options that need to be picked to make this block work are where should the feedback signals go into the device, where is the PWM coming out of the device, and what is your reference value for your feedback, and what is the definition of your switch node. So switching frequency and dead times need to be specified. So eventually, instead of diving into the peripherals and spending quite some time to set up all these different blocks, functional blocks, you now practically just configure the entire system on a very high level by just using physical values coming from your very application. So now if we've seen the basic concept of this MCC SMPS library, I would say just let's give it a try and configure a switch mode power supply. So for that purpose, I take my starter kit, then I plug it in with using the micro USB cable. And what happens now when I do this, when we look into MPLAB X, as soon as the tool connects, we see the product page coming up. So MPLAB X is detecting the board, and the board comes with a specific feature that it mounts a thumb drive on which all the information is stored that is now displayed in that window. So now from that window on, you can directly click on go to the kit homepage, and on that development kit homepage, you find all the documents and collaterals we offer with the device. So as of today, what you find is a user guide for the kit, the configuration user guide for the switch and power supply libraries, which includes the installation process, the library itself. Should it not be already included in your MPLAB X installation, you can always download the latest version from that website. And then you find further documentation like schematics and the detailed datasheet of the chip we are using, which is in this case the PIC16F71779. Good. So let's get started. So to set up a power supply controller on that chip, what I do first is I create a new project. So I create a standalone project, continue, I pick the device I'm using, which is PIC 16F1779. Click next. Now I have to check where my tool is, and here I find the CIP hybrid power starter kit. So I select this one, click next, choose my compiler, and then I need to give it a project name, so I call this CIP HP test, choose a directory, and click finish. So now within this new generated project, I'm now opening MCC. And as soon as the MCC modules have loaded, I can save the configuration I'm going to build in a specific file, which is usually stored in the project directory. So the very first thing, and this might be a little bit out of the scope of normal power supply designs, is I have to determine which frequency I would like to have running on that device. So to make sure that all the peripherals, including PWMs, interrupts, input capture, UARTs, and everything else you might use in your application works at a decent performance, we pick the 8 MHz oscillator, and we enable the PLL, which then gives us an effective CPU frequency of 32 MHz. So based on that timing, this is the base for all the other timings we are going to set up on that chip. So later on in the modules, we will find specifications for switching frequencies, for dead times and so forth. And all these timings always refer to the specific frequency we have set in this window. So from that point on, we are ready to go and dive into the configuration of the power supply peripherals. So to make our life easy, we are now referring to the Switch from Power Supply library. So when we look into the device resources, we find here this SMPS power controllers. So when we open those, then we find either sub-blocks, or the highest level would then be power supply topologies. So when you recall that diagram we have just seen, at the bottom there were all the peripherals, then above there were already pre-configured sets of peripherals forming modulators and compensators. Above that we found encapsulated blocks for control modes, and above that there was our topology. So we're going to start at the highest level, let's say this highest abstraction layer. And as we see, there are a couple of different topologies already we can pick from. In this case, we pick a generic synchronous buck converter. We double click it, and now it's loaded into our project resources. When we load that project item, then first we end up in a short page with some short description about what this block is all about. The second one is then our configuration window. So, and if you consider the number of peripherals we would have to put together for one PWM controller, so all of that is now already pre-configured. So we know exactly which peripherals we need to pick, how they need to be interconnected, because we know what you are going to design. So the number of parameters that need to be set now comes down to a very, very short list. So this now starts with the switching frequency. So for this particular starter kit, we pick 500 kilohertz. The maximum duty cycle, this determines some certain clamping value. So for that starter kit, it is 90%, but it's really highly application dependent, and it really depends on your topology and your safety levels you're trying to achieve. So we leave it at the 90% for that, for our demo setup here. The reference voltage relies on your feedback signal. So The voltage divider we used on the starter kit gives us feedback signals of exactly 2.5 volts when the converter is producing 3.3 volt at the output. So to achieve that 3.3 volt stable output control, we need to set the reference at 2.5 volt. Then we have a leading edge blanking. And that depends on the current feedback we are going to use. So the starter kit offers 3 different current sensing options. The first one is a current sense transformer, which is located above the high side switch. So when we switch over into the third top, then we see a simplified schematic that gives us some indication where we find our current sensing option and how feedbacks and interconnects are done. So here we see that complementary PWM that's connected to the high side and low side switch of our half bridge. Then the current sense gives us the inductor current. So the first option would be, this is the one we're going to use, would be the current sense transformer. So that guy is located here, just before the high side switch. That location that is indicated here is just idealized, indicating that we are always measuring the inductor current. In truth, the second option would be the shunt, which is located between the inductor and the output capacitor, so at this place. And then we have a third option, which is called DCR sensing. So we are using a parallel RC network, which is sitting in parallel to the inductor, and that would actually give us that indicated current position. Although this is more an emulated current feedback signal, it's still precise, but is lossless because it's not sitting really in the power path, so it doesn't create losses. That is the advantage of DCR. The penalty is it's not that accurate. So the 3 different current sensing options have 3 very different characteristics. So the advantage of a current sense transformer is that it's very fast and it gives you a very nice resolution. So it's a large signal, so the signal noise ratio is very good. The downside is, because it's located above the high side switch, is that we only see half of the current waveform. So we only see current feedbacks when the switch is closed and current is flowing through that current sense transformer. So we don't see the discharge current towards the load and the output capacitor. The second sensing option, the shunt, has the advantage that it shows us the entire current waveform. However, the shunt needs to be very small to create as little losses as possible. So we need to amplify that signal to get it up to a size that we can actually work with it. So this is done with a high side current sense amplifier. These amplifiers have limited bandwidths, which usually results in a tiny phase shift and usually some damping on the amplitude. So instead of a razor-sharp triangular current waveform, you might get something that's a little bit more sinusoidal and phase shifted. The third option, the DCR sensing, is equally sensitive, so the signal won't be very large. So we also need to amplify it. And it is a signal which also needs to be taken from the high side. So we need a high side or higher voltage differential amplifier. So the advantage in this low voltage buck providing 3.3 volt is that the output voltage is still below the supply voltage of our device. So what we can do now is we can utilize an onboard amplifier as differential amplifier for the DCR sensing. So these are the 3 options we have. In this first configuration, we will start out with a current sense transformer. So the current sense transformer has a very particular signal waveform. So every time the switch closes, it creates a tiny spike. So we see a turn-on spike, and the peak of that spike might be higher than the peak our peak current mode controller is triggering on. So we have to make sure that this peak is not accidentally tripping our comparator. We're achieving this by setting up a so-called leading edge blanking window. So this time frame we are setting will disable the comparator during that time between the start of the cycle until the end of our leading edge blanking period. So when we are going to set this up, okay, on this particular design, we know already it needs to be 250 nanoseconds. So the 250 nanoseconds are counted from the point our internal PWM module is generating the leading edge. So there's the first delay we have to consider is the delay between our signal generator and the propagation delay through the complementary output generator logic through the pin driver towards the MOSFET driver, the propagation delay of the MOSFET driver, until the MOSFET eventually turns on. So that delay is already 55 nanoseconds, and then we see that spike of that current sense transformer, and the width of the spike is roughly 120 nanoseconds. And to be a little bit on the safe side, to account for additional switching noise, we add some safety margin. And this altogether, that delay chain, that brings us up to 250 nanoseconds. So the third setting we have to make is dead times. So we have a half-bridge converter. That means when we are closing both switches at the same time simultaneously, we are practically shortening out the input voltage, and that will potentially or very probably blow our switches. So we have to make sure that this never ever happens. This dead time setting is based on a high resolution delay line, which is part of the complementary output generator. So we can adjust dead times with a resolution of 5 nanoseconds per tick. So when we set up a value of 3, then we get 15 nanosecond dead time. So here in this mask, all the values we are entering are physical values, so using physical units. So in this case, we are just entering 15 nanoseconds. If you try to enter 12, it might sit there with 12, but eventually will just be 15 anyways. So your choices are 5, 10, 15, 20, and so forth. So the rising edge with 15 nanoseconds sounds very short, and that the reason why the dead time needs to be so short is the MOSFETs we are using on this starter kit. So these are high-speed silicon MOSFETs, which turn on in roughly 8 nanoseconds. So between 5 and 8 nanoseconds is the typical rise and fall time of these MOSFETs. So they're extremely fast, and the edges don't show any Miller plateau or any additional delays. So we can position them very close to each other to ensure a most efficient operation of our power stage. So the rising edge is 15 in this case. The falling edge dead time is named with 60 nanoseconds. So the mismatch between both dead times also mainly come from that delay between our signal generator edge through the entire output logic, MOSFET driver delays, and then we have to account for all these additional delays in addition to our appropriate dead time setting. So the best way to figure out what the appropriate dead time is always starting out with a very safe setting, which is usually derived from the data sheets of the components you're using. So look into the data sheets of the MOSFET drivers, try to figure out what the propagation delay is there, look into the MOSFET data sheets, look for the typical rise and fall times when driven by a driver at a certain voltage, and then you get some good ballpark number where that dead time might be. Add a little bit of safety margin and fire up your power supply for the first time, look at the scope, measure it, and optimize it. So this is the more typical, little bit pragmatic, but let's say useful way in setting up these values. Good, so once we have gone through that list, so now the last setting here would be the slope compensation. So slope compensation is not available yet because we first have to have a peripheral which we need to program. So at that point, there's nothing else we can do. So now we have all the settings we need to at least set up the architecture. We're doing this by selecting 1 out of 4 PWM controllers. So the peak current mode controller is located here in a specific corner of the device. So the pinout of the device is divided in 4 sections. So in here on the upper left, this is where we find the in and outputs of the first PWM controller. Then here is number 2, number 3, and number 4. So that pinout has been arranged in a way that when you're designing multiple power supplies, that you can route the signals onto the device in the most ideal way without crossing other lines, especially trying to keep analog separated from digital and so forth to prevent any conflicts with signal integrity. So on the starter kit, the peak current mode control is wired up to PWM controller number 3. So I pick that one from the list, and now I can upload all the modules that are required. So I'm uploading the configuration for all the peripherals. So this takes a moment. And here we are. So now in the project resources, we see beside that one power supply topology we have added first, there is now a list of peripherals. So now we see all the sub-blocks, which is then here, for example, the comparator, digital to analog converter, an op-amp for the air amplifier, our fixed voltage reference, the complementary output generator, the ramp generator, and the basic switching PWM. So, and as you can see, every time I click on one of these modules, I see all the configurations which are available for that particular peripheral. So if you go into the register map, you see this, there are endless options of configurations that could potentially be done. But as we have done all that already, all these settings have been done for you already. So I can just skip that peripheral level, go back into my sync rectifier, and now, as a DAC is loaded and I know what the resolution of that DAC is, now we can set a slew rate of our slope compensation ramp generator. So for that particular design, we need a slope of 0.35 volt per microsecond. So that ramp that is modulated onto the reference of the air amplifier now decreases over time with a ratio of 350 millivolt per microsecond. So now we are all set. So I save my configuration and now I generate the code and I watch the output window until the process has completed. And I see this is done first when the progress bars have disappeared and when I find a line that says saved configuration in file my path. So when I now switch over into the project and I open the header, then I see that the MCC generated files folder in which all the switch and power supply configurations have been generated to. And then there's another folder called SMPS. And in this folder, I find software functions that already have been generated in addition to the basic peripheral configurations. So what we're providing as a standard generated code block is a soft start routine. Especially in half-bridge configurations at higher input voltages, if you would just snap on the PWM with a certain duty cycle, the chances are very high that you will just blow up one of your switches. So usually half-bridge drives, especially with high-speed MOSFETs like those, vitally need to be soft started. So, and that code is now part of your project already. So this is a function you can call directly, and you don't have to be concerned about your soft start behavior anymore. So when we go into the source files, we find also a main, which contains the main program, and here's our MCC generated block with all the peripheral configurations, and here also the switch mode power supply software function blocks. So when I look into my main, the first line within main is system initialize. So inside that system initialize, I see the configuration of my pinout the oscillator settings, watchdog timer settings, and then all the peripherals for my switch and power supply PWM controller, including the two sync buck and PCMC block software blocks, which include the soft start. Within main, there's nothing else to find. So there's just a while loop. So the only modification we have to do manually is to decide when that power supply should be turned on. So where to place my soft start function call. So the first thing is we have to figure out how that function is called. So we have to go into the PCMC header to learn how that function call looks like and how it's named. So it's called PCMC underscore soft start. Easy to remember. And we would like to soft start that, or to start the power supply immediately just before we enter the while loop. So I place that function call here. And this is it. Now we are ready to go. So now I hit compile. So compile the project. Just to make sure that the generated code doesn't produce any errors. And I get a build succeed, and now can program my device. Okay, so now we see programming verified complete, so the program has been successfully programmed. Okay, so now here we are with a programmed board. Now we have to test if it's really working. Now I'm connecting this board to the power supplies and the load, which is part of that development kit. So for that purpose, I'm stealing the input voltage from that input terminals and connect it to my freshly programmed board. And I take the load module we have here on this side and connect it to the output. And then here on the display, we see an output voltage of 3.3 volt at already close to 4 amps. So regulation seems to work. To make sure that it's really working, we are just changing the load, turning it off, and it's still regulating to 3.3 volt. So seems that we have an active controller that controls the voltage to a constant level over load. How well it really works, our controller, what the eventual performance is, and our bandwidth and the transient response, that obviously requires a little bit of more thorough analysis. And for that purpose, we have a network analyzer which is connected to that kit. So I will just remove these plugs again, give it a plug the load module back in. And the software which is currently running on that kit and that kit is identical. So this is exactly the same basic P-card mode controller we have just generated. So when we are now letting this board run, then we have on this side our network analyzer is running, and it's continuously measuring the loop. So the way we do this is that we have a tiny resistor on top of our output voltage divider. So voltage dividers at the output have usually resistors in the kilo ohm range, and we put a tiny 10 ohm resistor on top of this high resistance. And then we use an injection transformer. So this is a one-to-one current transformer. And that is connected to the signal generator within our Bode analyzer. So this frequency now is applied to the primary winding, is injecting a current that current is then showing up on the secondary side and is injecting an error signal in that 10 ohm resistor on top of our voltage divider. So this artificial error signal is now traveling through the voltage divider, is entering our feedback loop at the error amplifier. The error amplifier starts to respond to that error signal and is injecting this error into our modulator. And so our PWM starts to modulate against that error that is showing up at the feedback input. And so our output voltage starts to change. So the network analyzer now looks at the signal that has been injected on one side and then looks at the output of the power supply on the other side of the 10 ohm resistor and just measures the sinusoidal response of the system and measures the difference in amplitude, which gives us the gain, and the phase shift, which gives us the phase, and plots it as a Bode plot. And the Bode plot then allows us to do a stability analysis where we can measure the crossover frequency, the slope of the gain at the crossover frequency, the phase at the point when the gain hits 0, and the value of the gain when the phase hits the minus 180 degree sole point of instability. So the so-called gain margin. So then with phase margin, gain margin, and crossover frequency, we now have all the parameters that determine the total bandwidth and performance, basic performance parameter and stability of our power supply. So before we have a closer look at the measurement, let's briefly revisit what we are actually going to measure. So this is a block diagram of our system consisting of the power plant, which is the transfer function G of S in the S domain. And then we have the second transfer function, which is our compensator H of S in the S plane. So our feedback in our system is closed with a voltage divider, and this feedback signal is then fed into the compensator, is then comparing this into a reference, and the difference is then applied by our modulator to the plant. And that changes when we change the duty cycle. For example, the output voltage goes up or down, and any transient that might hit the system from outside or low transients or from the input will then be compensated by our control system. So to make sure that this system is stable, we have to have a look at the total transfer function of this entire block from input to output. And this is the gain, the closed loop gain. So G closed loop equals the plant gain over 1 plus the plant gain times the compensator gain. So when we look at this term, then one thing becomes obvious. That thing is always stable as long as G of S times H of S is different than -1. Because imagine when this tends to go to -1, then we have 1 plus -1. This goes towards 0, so the gain of the system will go to infinity, which means that the system is getting out of control and the gain becomes infinite, and the system is gone and will most probably blow up in our case. So this is why we call this G of S times H of S equals -1 is the sole point of instability. So in any other condition, the system is de facto stable, and only in that point it becomes uncontrollable. So when we are making a stability analysis, the whole stability analysis is now about how far are we away from this sole point of instability. So, and this is the so-called open loop gain within the closed loop system. So while the system is operating in closed loop, we are only having a look at the open loop gain of the system. So now when we have a closer look at the Bode plot. So what you're seeing here is a continuous measurement of the open loop gain in the closed loop system. So this term of open loop in a closed loop system comes from the open loop component that looks for how far away are we from the sole point of instability, which is the point when the system hits a phase lag of minus 180 degrees. So in this region, the system should not be able to respond to any transient in any reasonable form. So we need to have a large negative gain in that region. The body measurement is, has always, when we look at the phase, there's always one kind of misleading thing about the scale of the phase, and this is the minus 180 degree line is actually a 0 at 0 degree phase in that body plot. The reason for that is that the small signal model defines that minus 180 degrees at the reference of the system. However, the measurement now is done at the output of the power supply, so the other side of the aisle. And then we have that phase lag of 180 degrees throughout the system. Doesn't really matter, it's just if you're wondering why we're always talking about minus 180 degrees as sole point of instability, and here in that scale we look for that point at 0 degrees. That's actually the same thing. So what that body plot here in an active measurement is showing you is actually more tuned towards stability analysis than a theoretical description of the system. So that is the only thing that's maybe interesting to keep in mind. So let's perform a measurement. So as you see, it's running here at the low frequency range. We see a lot of noise. And that is the small signal model. So you achieve best and most accurate results of the transfer function when the signal you're injecting is as small as possible, so that you don't drive some components, like especially the error amplifier, into nonlinear regions at its margin of its total input range. So this is why we always try to keep that injected error signal as small as possible. And at low frequencies, this is getting tricky for the measurement equipment to see the variation of the sinusoidal curve that is so small that the noise floor starts to have a large influence on the measurement results. So this is why we see in the low frequency range it's always very noisy. So luckily that measurement tool we're using here, the Bode 100, has a feature that allows us to shape the gain of our input stage so that we can increase the gain to reduce the noise. But as you see, it is maybe good, but still not good enough. So we would have to perform many measurements of exactly the same operation point and activate an averaging over that period to get rid of that noise to also achieve a better, more accurate result in that region. But for the moment, we are not really interested in this low frequency range. We are more interested in the total performance of our feedback loop, which is more about stability. So the stability criteria we are now looking for starts with the crossover frequency of the gain. So where does the gain, which is the red line, cross 0 dB? So this is pretty much exactly at 30 kilohertz. We can make a more precise measurement if we go here into the scale and say, okay, please give me the number at 0 dB. And then we see exactly it's at 30.116 kilohertz. The other point that's important for the stability criteria is the gain margin, which we find when the phase, which is the blue line, now hits minus 180 degrees, or in our plot, 0 degree line. So we do the same. I go into that table, put it to 0, and the cursor gives me the number of minus 14 dB, which is a sufficient gain margin for a power supply. So when we are, let me stop the measurement to keep it more quiet. So now when we analyze it, one of the third stability criteria we would look for would then be the slope of the gain at the crossover point. So ideally it should be minus 20 dB per decade. So we're looking into that decade. So here we have a point which is very close to 10 dB, so that is easy to take. And then it should be a linear minus 45 degrees or minus 20 dB per decade slope. And when we draw a line, or we imagine a line that has a slope of minus 20 dB per decade, then it would be at minus 10 dB at 100 kilohertz. And the crossover point would right be in the middle of that slope, so we exactly hit that slope of minus 20 dB per decade. So it's a perfectly schoolbook stable system. So the last, and for most designers, most important value would then be the phase margin. So that is determined to be at the crossover point. So what's the phase lag at the crossover point? So we take that cursor, and we find, when we, let me reset this to 0 again. So we find a phase margin of 60 degrees, gain margin of 14 dB at a crossover frequency of 30 kilohertz. And we are meeting, so we have really good stability at the crossover frequency, so phase margin, gain margin, and the slope at the crossover frequency. All three major stability factors are in a really good region for a real stable power supply. So the bandwidth we have set at 30 kilohertz is a little bit, at maybe a 15th of the switching frequency, which is also a good ratio and which allows us to have enough safety margin to account for variations in inductor component values, capacitor component values, and so forth. So what we have covered today is, so you saw a short introduction of the CIP hybrid power starter kit, our demo setup, the design procedure using our switch from power supply libraries in the Microchip code configurator, and finally how we generate the project. We build our PWM controller, download it into the device, bring it into the system, and then measure and analyze it. So I hope also that the measurement results have given you some idea about the performance level you can expect from the analog peripherals on board of these chips. It is really a straightforward PWM controller as you can expect it to find on any other ASIC in terms of performance. Nevertheless, have a look at the datasheet, and every further information you can find on the descriptions below. Just click on the links, follow them, and you will find all the documentation about the board, the devices, the switch from power supply libraries, and further information on generic topics of simulation of switch from power supplies and design practices. Thank you very much for watching. Hope to see you soon.